Today we are going to be talking about the frequency response of our single stage op amp because we need to understand what that is before we can learn to compensate for it. And so to that end, we are going to do a very brief review of the capacitances that occur in a MOSFET because those are going to be the guys that we'll be dealing with. MOSFET. High frequency. Capacitances. So if we took a look at a MOSFET transistor during saturation, we would have something that looks like this. Here is our substrate. We have an N+ region that is serving as our source. We have some sort of metal contact here. There's our source terminal. Similarly, on the opposite side, our N+ region and our metal contact that allows us to apply a signal to the drain. We have an insulating layer here. We have our polysilicon gate. And I know very explicitly that this is not where the body terminal is going to be, but we are going to pretend that it's back here for now as a sort of back gate, right? It obviously would be formed inside of a P+ implant and all that kind of good stuff, but I don't want to deal with that right now because it's going to take too long to learn what's going down here. And we will have a channel. Like so. And so because of the depletion region formed between the N+ active layer and the body, we will have some capacitance CSB and some capacitance CDB. We will have a capacitance CGS forms between the gate and the source. And we will have a capacitance, let's call it CGD, formed between the gate and the drain region as well. So those are two different capacitors because of the profile of the channel during saturation region operation. I'm not going to go into how to calculate all these things and all this kind of stuff, just trying to tell you where these capacitance come from. How that affects our small signal model is as follows. So we will have a gate terminal G. And then some capacitance CGS. Here's our voltage VGS Here's our current source, GM, VGS. Body effects are included. This will be GMB, VBS here. We have our output resistance, R out. Let's see, between the source and the body terminal, we have that capacitance CSB, over which a voltage drop VBS occurs. Between the drain and the body, we have that capacitance CDB. Here is our source terminal. Here is our drain terminal. And our last capacitance occurs between the gate and the drain, so that guy's going to be right here. So this is CGD. All right, so in our single stage op amp, where we have a NMOS differential pair loaded with a PMOS current mirror, will body effects be present? Short answer is no, not at all, right? So that means this current source is going to go to 0 because these terminals are shorted together. And since those terminals are shorted together, that means CSB is shorted out. So we'll only have CGD, CGS, and CDB to account for all of the transistors in our model. All right, so with that in mind, or I guess I should give you guys more than 2 seconds to write things down. All right. So with that in mind, let's look at high frequency response of common source amplifiers first. And we're going to look at 2 amplifiers in particular. And the reason why we're looking at these 2 should be very apparent very quickly. Our first is going to be a common source amplifier where we load, sorry, this should be a PMOS transistor. Our common source amplifier with a PMOS current source. So here's VN, here's V out. This will be transistor M1. This will be transistor M2. So what this guy really symbolizes is the right-hand side of our single stage op amp, right? Where we have some DC gate voltage that's getting applied to transistor M4, causing it to do certain things. And this is where we would apply our input signal on the right-hand side. So we're looking at this common source amplifier for a very, very specific reason, okay? So this is our generic model. Now let's throw all those capacitors in. So we're going to have some capacitor here. So this is between the gate and the source. So this will be CGS2. We'll have a capacitance here that will be CGS3. GD2. And we'll have a capacitance here. That will be CDB2. And we'll have those exact same three capacitors for transistor M1 as well. CGD1, CGS1, and CDB1. So our goal is to figure out what the frequency response of this guy is, which is going to be summarized by its transfer function, or the transfer function, for those of you that don't remember, the H of S, and it is simply the output voltage as a function of frequency divided by the input voltage as a function of frequency. So effectively, we're looking for the voltage gain of this guy, where these capacitors have an impedance. Okay. So our small signal model will look like this guy here. Bring this closer to me. So this is my source of M2. This is my drain for M2. This is my gate for M2. This guy is CGD2. And this guy is where BSG2 occurs. That's my PMOS bit taken care of. Down here for my NMOS, I'll effectively have the exact same thing, except that my gate voltage will no longer be tied directly to ground. GM1, VGS1 goes here. CGS1, CGD1 goes here. This is where VGS1 occurs. This is the drain of one, the source of one, ground. And here's where our input voltage is applied. All right, so let's take a quick moment here to figure out what's going on. Right. So by inspection, what is BSG2? Zero, which means this current source doesn't. And we can also say that since VSG2 is 0 volts, this capacitor is shorted out, CGS2, and so it won't contribute anything. So between our drain node, which the two drains are tied together, and the ground, we will have R out 1, CDB1, CDB2, CGD2, and R out 2. So effectively, I'm going to redraw this with all of those impedances from up there, put in parallel with this stuff down here, because they're all literally in parallel with the bottom part. So our simplified version will look something like this. What the hell just happened there? So this is going to be CGS1, CGD1, GM1, VGS1. Here's where VGS1 is. I'm going to call this resistor R out 1 in parallel with R out 2. And I'm going to call this capacitor here CDB1 in parallel with CDB2 in parallel with CGD2. And then here is our output node. Yeah. So to make the math less horrifying, I'm going to lump these three capacitances together. Call it C out. And I'm going to lump these two resistances together and call this RDS, since it's a resistance between the drain and the source. Okay. So we have two options here for our analysis. And the reason why this analysis is going to be a little different than what we've done previously, in this class anyway, is the presence of that feedback capacitance, which is linking the input signal to the output signal, right? So that CGD1 here messes things up. So we have two options. We can either effectively write KCL at the input node, KCL at the output node, and then do a whole bunch of substitutions and make it work. And we will have two poles that are linked together with lots and lots of ugly math. Or we can use Miller's theorem to split that feedback capacitor up into 2 bits. That makes our lives much more simple. So I'm going real hard on option 2 because I don't want to do an hour's worth of math to get nowhere close to where we want to be. Okay. So if we apply Miller's theorem and split that capacitance up, what we're going to have is a system that looks like this. So this is going to be CGS1. This is going to be CGD in. So that's the portion of CGD1 that gets referred to my input node. Then over here, I'm going to have GM1, VGS1 in parallel with what we've called RDS, in parallel with what we've called C out, in parallel with CGD out, which will be the portion of CGD1 that gets referred to the output. All of these share a common ground node. Here is where V out is taken. And using Miller's theorem, 1 over S CGD in. The impedance that we see at the input side will be 1 over SCGD1 times 1 minus the gain. This is a common source amplifier. And so in this case, the gain will simply be GM or negative GM times what I have described as RDS. Does that make sense? Okay. So 1 minus negative will give us 1 positive. So GM1 RDS, which means that CGDN is CGD1 times a factor of 1 plus GM1 RDS. And I'll just sneak that one down here, apparently. 1 over SCGD out will be SCGD1 multiplied by a factor of 1 minus 1 over the gain. GM1 RDS, which means that CGD out is equal to CGD1 times 1 plus 1 over GM1 RDS. Everybody catching what I'm throwing thus far? Okay. So just using Miller's theorem to split CGD into two capacitances so that we have an easy transfer function to figure out here. So what should V out be? Oh, I forgot one thing here. Hopefully it's obvious. This voltage is still VGS. So if we look at this guy, recognizing that Vn and VGS1 are literally the same quantity, we should be able to see that V out is just going to be negative GM1 times Vn times these three impedances in parallel, right? So we will have V out as a function of S frequency will be negative GM1 times Vn multiplied by RDS divided by S over C out plus CGD out. So effectively what I've done here is I've just lumped those two capacitors in parallel into a single equivalent capacitance. And then I'm just doing the Z1 times Z2 over Z1 plus Z2 method of getting the equivalent impedance of that parallel combination. And I can call this negative GM1 Vn multiplied by RDS divided by 1 plus S RDS times C out plus CGD out. Like so, which lets me define my transfer function very easily. So it's going to look like negative GM1 RDS multiplied by a factor of 1 over 1 plus S RDS multiplied by C out plus C GD out. Where, put plots around these guys. This guy on the left-hand side here is my DC gain. It's really the mid-frequency gain, or the mid-band gain, but because we don't have anything to cause, we don't have any capacitances that we're dealing with at the input, this should extend all the way to DC effectively. And then we have our frequency response portion, or the bit that starts acting up as the frequency increases. So for very low frequencies, all this bit on the right-hand side here goes to 0, and the amplifier behaves exactly like we would expect it to. As the frequency begins to increase, then we see that it starts to get shaped, and we have some sort of phase shift and all that kind of good stuff in because we have capacitors. We have a pole for our transfer function, omega p, and I'm just going to call it omega p out because it's obviously associated with our output node. And so let's call that 1 over RDS times C out plus C GD out. And circling back around, if we substitute all of our stuff in, that's going to look like R out 1 in parallel with R out 2 multiplied by CDB1, CDB2, CGD2, CGD1 multiplied by our Miller factor of 1 plus 1 over the gain, GM1 times R out 1 in parallel, R out 2, close parentheses there, close parentheses there, close bracket there, and it's 1 over that whole big ugly thing. All right, so we have a single pole system, and the capacitance that was referred to the input doesn't affect our frequency response at all, right? Everything that we have here is the crap that's been thrown to the output side, okay? That's going to be very important because it's going to make, when we analyze our op amp, it's going to make things much, much easier because we don't have to look at any contributions from our input nodes. Okay. So any questions on this? All right, we're about to repeat this. I'm not going to do all the work, but we're about to repeat this for the left-hand side. All right, so if we have common source amplifier, but this time it is loaded with a diode connected transistor. So let's call this guy BN. This is our output node, the out. So this is obviously representative of what the left-hand side of our op amp is going to look like. And so we will have following capacitances. So we're going to have C GS2, CGD2, and CGD CDB2 here. CGD1, CGS1, and CDB1, like so, right? Excuse me. So one thing that we should be able to see right off the bat is that CGT2 is shorted out because it's literally in parallel with a short circuit. So when we draw our small signal equivalent, I'm gonna throw that one away. So our small signal circuit is going to look something like this. So here's CGS2, GM2, VSG2, parallel with R out 2, parallel with CDB2. Here is the source of transistor 2, the drain of transistor 2, and over here is the gate of transistor 2, and the gate and drain are tied together because this is a diode connected transistor. This is VSG2. Now we'll come down here and take care of transistor M1. GM1, VGS1, R at 1, CDB1, CGD1, CGS1, D1, this one, ground, and UGS1. Yeah. All right. So for this guy, obviously that current source, which supplies GM2 times VSG2 of current, has a voltage drop of VSG2 over it, which means it looks like a resistor having a value of 1 over GM2. We discussed that in class the other time. So effectively, looking up, we have R out 2 in parallel with 1 over GM2, in parallel with CSG2 or CGS2, in parallel with CDB2. And so we're going to get a very similar looking circuit if we simplify this guy, right? So we'll have something like this. CGS1, CGD1, this resistance right here is going to be R out 1 in parallel with R out 2 in parallel with 1 over GM2. This capacitance here is going to be CDB1 in parallel with CDB2 in parallel with CGS2. Oops, don't know what happened there. Here is B out. So if we call this resistance RDS and this capacitance C out, I need to make note that this is VGS1. This is literally the exact same thing that we just looked at. So I'm not going to bother analyzing it again because we just did it. So this is obviously then going to have the same transfer function and everything, and we're going to wind up finding out that we have a pole omega p out here. When we substitute in our values for RDS and C out, that is going to look like R out 1 in parallel with R out 2 in parallel with 1 over GM2 multiplied by CDB1 plus CDB2 plus CGS2 plus CGD1 times 1 plus 1 over GM1 R out 1 in parallel with R out 2 in parallel with 1 over GM2. And then 1 over that whole thing. So the analysis is identical. You get different poles because there are different capacitances and different resistive portions, but they behave extraordinarily similarly, which they should because they're both common source amplifiers. Anything wild or crazy there? All right, so I'm good to move to the next bit. All right. So now that we've done those two things, so that effectively, we know how both halves of our single stage op amp should behave. Let's consider the single stage op amp. As a discrete circuit. Let's see, frequency. So the circuit that we are going to be analyzing is this guy. I'm going to call this guy right here node Y, this guy right here in our output node Z. Out. DB, this will be M3, M1, M4, M2. Call this guy node X, and here is our biasing transistor M5, where we have some voltage V bias 5. Okay, So I'm about to identify all the capacitances and all that crap on this guy, and I want you to not do it because you're going to wind up erasing practically everything I'm about to write. All right. So obviously, we'll wind up having all of these capacitors. I'm not even going to really bother labeling them. You're writing these down, you're doing it wrong because we're really just going to erase all of them in a minute. So these are all the capacitors that survive the fact that we don't have body effects to worry about. Oh, crap. All right, so let's start by talking about the transistor, the capacitance associated with transistor M5 first, okay? So we know from last class meeting that our circuit is essentially symmetrical. It's not fully symmetrical, but it's pretty close. From that, node X is still going to serve as a small signal ground, which means that since V bias 5 is a DC voltage, this capacitor here, this would be CGD, is grounded at both sides, so it goes away. CGS is going to be grounded at both sides. And since our drain is ground and our source is ground, CDB is also going to go away. So literally none of those transistors contribute anything. That's only true, and I know this is going to sound weird, if we're at the low frequency portion of the high frequency spectrum. And so what I mean by that is this transistor is going to be big, which means those capacitances are going to be big. So they're going to look like open circuits for a really large portion of the frequency spectrum. Once they start to matter, what they are going to do is cause the common mode gain of the system to go up. So they're not going to have any effect on the differential mode portion at all, but they're going to start messing around with how this circuit syncs common mode signals to ground. So for our analysis, they're going to contribute nothing. Now let's look at all these other guys, right? So everything to the left is the second circuit we analyzed. Everything to the right is the first circuit we analyzed. And the capacitances on the input side didn't contribute anything to our frequency response whatsoever. So I'm going to say that we can throw all of these guys away and replace all those guys with a single capacitance CY, which is just the output capacitance for the left-hand side of the circuit that we dealt with earlier, right? So we know how to find it. This is just a shortcut. And we can do the exact same thing on the right-hand side here, right? We know that none of the capacitances on the input side really affect our frequency response whatsoever. And so let's say that we have some capacitance CZ here, where CZ represents the output capacitance of our PMOS current source loaded common source amplifier. Okay, so we've done all of the legwork. Now we're just simplifying things so that we don't have 15 capacitances to deal with. We have 2. Makes life a little bit easier, right? So this circuit with these simplifications will have the following small signal model. So this will be R out 3. This is GM3, VSG3. This node is the drain of 3. This is the source of 3. This guy will be ground. This guy over here is the gate of 3 and 4. This is GM4, VSG4, R out 4. This is the source of 4, which is tied to ground. This is the drain of 4. And so this is VSG3, which will be identical to VSG4. PMOS side all looks hunky-dory. NMOS side will go here. GM1 VGS1. R out 1. R out 2. GM2. Sorry, should write that on the inside. VGS2. Here's where node X was. We're treating that as small signal ground. Here's VGS1, where we apply VIDM over 2. Here is VGS2, where we're applying a negative VIDM over 2. Here's our output node Vout. And then I need to tie my gate to my drain over here, where this is D1, S1, D2, and S2. And so now I have to throw my capacitances in, which is really easy. Here's where CY lives, because this is node Y. Here's where CZ lives, because this is node Z. Everybody okay with this small signal model? All right, so the analysis that we're about to do here is effectively the exact same analysis we did yesterday, except that we have to take into account these capacitances. So we could say that we have a current of I1 flowing down and a current of I2 flowing up, where both I1 and I2 are GM1 VIDM over 2. Right. And I can say that they're both GM1 because transistors M1 and M2 need to be matched, right? Okay, so since the current source representing transistor M3 has a current of GM3 VSG3 over it, or excuse me, flowing through it, and a voltage drop of VSG3 flowing over it. That current source looks like 1 over GM3 again, which means Vy in this case is going to look like negative GM1 VIDM over 2 multiplied by R out 1 in parallel with R out 3 in parallel with 1 over GM3 in parallel with 1 over SCY. Everybody okay with that? So in class on Wednesday, we made the assumption that since 1 over GM3 is usually much, much smaller than R out 1 and R out 3, that's going to be the dominant portion. And so we're going to throw away the R out 1 and R out 3 bit again. And so what that's going to look like is negative GM1 VIDM divided by twice GM3 plus SCY, where I'm effectively just using the admittances of that 1 over GM3 bit and that 1 over SCY bit to get that result, right? So these two guys in parallel means that their reciprocal conductances are in parallel, and conductances in parallel have like resistances in series. And then I just use the 1 over bit because it's 1 over the resistance. Or we could do it the long way and actually do math, but that's much easier and you get the same result. Okay. So that's what Vy looks like. Now, this current here, I4, is going to be GM4 times negative Vy, because negative Vy is VSG4. Is that reasonable? So I'm going to, call this I4 is GM4 times negative Vy. And I can see that a current of I2 and I4 are both flowing into the input node, or excuse me, the output node, and they see a total impedance of R out 2 in parallel with R out 4 in parallel with CZ. So that tells me that V out is I2 plus I4 multiplied by R out 2 in parallel with R out 4 in parallel with 1 over SCZ. And so now math needs to occur, unfortunately. All right. So let's look at the I2 plus I4 bit. All right. So I2 plus I4 is going to look like GM1 VIDM over 2, which represents I2, plus GM4 times negative Vy. And substituting in negative Vy, this is going to give me GM1 VIDM over 2 plus GM4 times GM1 VIDM over 2 multiplied by GM3 plus SCY. Oops, everybody with me thus far? So far, I've only done substitutions from the other stuff that we know. All right, so the next thing that I'm going to do is I'm going to multiply the left-hand term by GM3 plus SCY over GM3 plus SCY so that I have a common denominator, right? So how far over? Middle of the 7th. So this is going to look like GM1 VIDM times GM3 plus SCY divided by twice GM3 plus SCY. So that's still just the I2 portion. And then over here on the right-hand side, it's still going to be GM1 VIDM GM4 divided by twice GM3 plus SCY. And so now, since both fractions have the same denominator, I can lump them together. And I am going to factor out a term of GM1 VIDM. And so that's going to leave me with GM1 VIDM multiplied by GM3 plus SCY plus GM4 divided by twice GM3 plus SCY. Everybody okay with that? All right, so what do we know about GM3 and GM4? They have to be the same thing if transistors M3 and M4 are matched. So finally, we could say that we would have GM1 VIDM multiplied by 2 GM3 plus SCY divided by 2 times the total GM3 plus SCY. So the numerator and denominator are similar, but they're not the exact same thing, because one of them has a factor of 2 SCY and the other one only has a factor of 1 SCY. And so it should be kind of obvious here that we're going to have a pole and a zero that are very closely related to each other. All right, so now let's look. We got the I2 plus I4 bit taken care of. Now let's look at what happens when we have R out 2 in parallel with R out 4 in parallel with 1 over SCZ. And I'm going to do this in a very specific way that will, the reasons for which will be obvious shortly. So let me scooch that down. This I don't have enough room. R out 2 in parallel with R out 4 in parallel with 1 over SCZ is going to look like R out 2 in parallel with R out 4 multiplied by 1 over SCZ times, or excuse me, divided by R out 2 in parallel with R out 4 plus 1 over SCZ. Multiplying through by a factor of SCZ over SCZ gives me a denominator of 1 plus S R out 2 in parallel with R out 4 times CZ. And my numerator will just be R out 2 in parallel with R out 4. Everything seemed groovy. Okay. So from this, V out will be GM1 times R out 2 in parallel with R out 4 times VIDM multiplied by a factor of, so my denominator is going to look like 2 GM3 plus SCY, and that's going to be multiplied by 1 plus S R out 2 parallel with R out 4 times CZ. And my numerator here is just twice GM3 plus SCY. So instead of writing all this down again, we could pretty easily see that our transfer function is just going to be the right-hand side divided by VIDM, which means this bit right here represents our DC gain, which is why I wrote it in this form so that we can literally see it's exactly what we got the last time, multiplied by our frequency response. Since this guy has a numerator that isn't 1, that means we have a pole. Excuse me, that's not right. We have a 0. Where omega z will be twice GM3 over CY. And then we're going to have 2 zeros. So let's call this, dang it, no, we have 1 0 and 2 poles. I'm sorry, my brain is fried right now. A pole at Y, which will simply be GM3 over CY. So this pole happens at exactly half of the frequency of the 0. This guy is commonly referred to as the mirror pole because it's the pole being contributed by the parent pair. And then we have a second pole occurring at our output, so omega p z, which is simply 1 over R out 2 in parallel with R out 4 multiplied by CZ, where CY and CZ, again, are the capacitances that we found in the previous examples. Okay. So our, and we can call this the output. So which one of these two do you guys think is going to be the lower frequency pole? Okay, well, I'll tell you, it's going to be the output pole there, okay? If we did a dominant pole approximation, or we did like the, gosh, so for high frequency, it would have been the short circuit time constant method for determining the poles, we would have wound up with something very, very close to this guy. So this is going to be our dominant pole, but we do have a secondary pole and a 0. And so what can happen, and we'll talk about this in depth on Monday, is that because we have a 2-pole system, we can see that our gain, if our gain doesn't fall to 0 dB before we hit a 180-degree phase shift in our signal, we have an unstable system. So effectively, this guy will work for low frequencies, but for high frequencies, our output is just the hottest of garbage. And so we have to learn how to compensate that. And so we're going to do that by a technique called pole splitting, which is effectively where we force one of the poles very, very close to the origin, and we push the other pole so far out that we hit our 180-degree phase shift before we get there, before the gain falls to zero. And so it's still technically unstable, but it'll be stable in a frequency range, a usable frequency range. So effectively, we're forcing it to be stable until we hit the gain bandwidth product. And then after that, who cares? Because it's not usable as an amplifier anyway. So that's what we're going to talk about on Monday.